What if I told you that NASA once studied a mysterious sphere, an object so unusual, so far beyond conventional physics, that they had to shut the entire project down? They called it the Buga sphere. At first, it seemed like just another experimental device in a laboratory. But then something extraordinary happened. When exposed to a high-energy particle beam, something scientists use all the time in physics experiments, the sphere didn't just deflect or scatter the particles like any normal object would. It absorbed them, completely. To some, it was the beginning of a revolution in energy research. To others, it was a red flag, a sign of forces we don't yet understand, perhaps forces we shouldn't attempt to control. And then, the research vanished. Files locked. Mentions scrubbed. The project classified, leaving behind only whispers. But what exactly was the Bugosphere? Why did NASA, or any scientific body, become so concerned after this bizarre incident? And what does it mean for the future of space exploration, energy research, and our understanding of the universe itself? Stay with me, because in this video, we'll explore the origins of particle beam research. How mysterious energy-absorbing materials have appeared in science before? The possible explanations, from advanced nanostructures to black hole-like properties, and why the Bugosphere might represent either the future of limitless energy or a Pandora's box we were never meant to open. This is not science fiction. This is science, theory, and history intertwined. Welcome to the mystery of the Bugosphere. Before we can understand what made the Bugosphere so strange, we need to step back. What exactly is a particle beam? A particle beam isn't like a flashlight beam or a laser pointer. Instead, it's a focused stream of tiny subatomic particles, protons, electrons, or ions, accelerated to nearly the speed of light. They're created in giant machines like the Large Hadron Collider at CERN, or smaller accelerators in labs worldwide. These beams let scientists probe the building blocks of matter, recreate the conditions just after the Big Bang, even test futuristic technologies like particle beam propulsion for spacecraft. Let's rewind to that fateful day. March 2nd, 2025. Eyewitnesses in Buga, a picturesque town nestled in Colombia's coffee-growing heartland, described a silver streak slicing through the clouds. No sonic boom, no debris trail like you'd expect from re-entering space junk. Instead, an erratic zigzag path, almost playful, before it touched down in a soybean field owned by local farmer Jose Ramirez. Ramirez and his wife found it embedded just inches into the soil, warm to the touch, but not scorching. It hummed softly like a distant beehive, he told reporters. No visible damage to the exterior. Just a perfect mirror-polished sphere about the size of a large beach ball, reflecting the sunset in eerie precision. Initial weight? Roughly 2 kilograms, light enough for one person to carry, heavy with questions. Word spread fast on social media. By dawn, locals had cordoned off the site. Colombian authorities arrived, followed by a team from the National University of Mexico, UNAM, yes, Mexico, thanks to bilateral science agreements in Latin America. Why UNAM? Their materials science lab in Mexico City boasts some of the world's best X-ray tomography scanners, rivaling NASA's own facilities at Goddard Space Flight Center. This wasn't panic or plunder. It was protocol. Secure the anomaly, document everything, and loop in international experts. Within days, the sphere was en route to a secure lab. Fun fact: Colombia's aerospace agency, CTA, has been ramping up UAP reporting since 2023, inspired by global pushes for transparency. Their hotline logged over 50 sightings that month alone, making Buga's fall feel less like a fluke, more like a pattern. But here's a punchy truth. In space exploration, falls from the sky aren't rare. Think China's Long March rocket stages raining down unpredictably, or the 2024 Starlink deorbit drama. Yet the Bugosphere? No matching orbital track on NASA's public debris catalog. Their spacetrack.org database, updated in real time as of October 2025, shows 0 hits for a 50-centimeter metallic object in low Earth orbit pre-crash. Date: March 2nd, 2025. Location: Buga, Colombia, 4 degrees 54 minutes north, 76 degrees 14 minutes west. Size: weight, approximately 50 centimeters diameter, 2 kilograms. Path: zigzag descent, no heat signature, initial temp, approximately 40 degrees Celsius, warm, not hot. Normally, when a beam of high-energy particles hits a surface, physics predicts what happens next: scattering, absorption in tiny amounts, or radiation. But never complete disappearance. This is why the Buga event was so baffling. Before we can understand what made the Buga so strange, we need to step back. What exactly is a particle beam? A particle beam isn't like a flashlight beam or a laser pointer. Instead, it's a focused stream of tiny subatomic particles, protons, electrons, or ions, accelerated to nearly the speed of light. They're created in giant machines like the Large Hadron Collider at CERN or smaller accelerators in labs worldwide. These beams let scientists probe the building blocks of matter, recreate the conditions just after the Big Bang, even test futuristic technologies like particle beam propulsion for spacecraft. Normally, when a beam of high-energy particles hits a surface, physics predicts what happens next: scattering, absorption in tiny amounts, or radiation. But never complete disappearance. The term Buga didn't come from NASA itself. It was an informal nickname, possibly originating from the location of early experiments, or even from researchers' inside jokes. What we know is this: the device was supposedly designed as part of an experimental material science project. Its goal? To test advanced alloys, superconductors, and novel lattice structures under high-energy conditions. But during one experiment, when the sphere was placed in the path of a directed particle beam, the unexpected occurred. The beam didn't scatter. It didn't produce secondary radiation. It didn't even heat the sphere up significantly. Instead, the energy simply vanished. To the observers, it looked as though the sphere was drinking the beam, like a sponge soaking up water. Enter NASA, the gold standard in space exploration. Their 2022 UAP study, culminating in a September 2023 report, NASA UAP Independent Study, called for rigorous, stigma-free science. Director David Spergel emphasized, extraordinary claims require extraordinary evidence. As of October 2025, NASA's ARO, All-Domain Anomaly Resolution Office, has analyzed 800-plus cases, finding 2 to 5% truly anomalous, like transmedium travel-defying drag equations. Buga connection? None direct. NASA's site shows 0 mentions per their transparency portal. Goldstone radar, scanning LEO daily, detected no pre-crash signature. Yet whispers of collaboration persist. UNAM's Velasquez hinted at international consultations in a La Jornada interview. Theoretical: if particle beam tests occurred, rumored in fringe reports, unverified, it'd echo NASA's 1980s Charged Particle Acceleration experiment on shuttles. Beams probing plasma, not weapons. No shutdown confirmed. Sensational claims of absorption lack evidence. Physics basics: absorption equals heat/reflection/destruction. Hold, per Science. 2025 review. NASA's stance? Send it to Galileo Project for independent scans. Loeb's team hunts interstellar artifacts with $2 million funding. Historical anecdote. Remember Roswell 1947? Debris from Project Mogul balloons? Buga could be similar, a balloon probe or defunct CubeSat. Astronaut Mae Jemison, first black woman in space, shared in a 2024 TEDx, "Anomalies push boundaries. They got me to the stars." Comparison: Earth versus Cosmos. Our planet's gravity well traps junk. Space's vacuum lets oddities wander. Implications: better tracking via SpaceX's Starshield constellation, launching 2026. That should have been impossible. Now, let's be clear. Extraordinary claims require extraordinary evidence. Since NASA has never officially released detailed findings, we have to explore the possible scientific explanations. Advanced metamaterials. Metamaterials are engineered structures that can bend, absorb, or redirect waves, including electromagnetic and particle waves, in unusual ways. Perhaps the Buga sphere used a layered, lattice-like design that absorbed the beam's energy into vibrations or heat we couldn't easily detect. Superconducting plasma traps. Some theories suggest it could have been coated with superconductors that created magnetic fields strong enough to trap incoming particles. Instead of bouncing away, the particles spiraled inward and lost their energy. Miniature black hole effect. Speculative. What if the sphere created conditions where particles slipped into a temporary energy sink, similar to how a black hole consumes matter? While highly theoretical, it would explain the disappearance effect. Quantum energy transfer. Quantum field theory allows for strange resonances. Maybe the sphere resonated at a frequency that allowed energy transfer into the vacuum, effectively canceling out the beam. Each of these is fascinating, but none are fully satisfying. So why would NASA, or any organization, stop research like this? After all, imagine the possibilities. Energy storage beyond batteries, radiation shielding for spacecraft, even propulsion systems that could one day carry us to Mars or beyond. The official reason was never released, but scientists speculate on three possibilities. Safety concerns. If a device can absorb high-energy particle beams, what else can it absorb? Could it destabilize lab equipment, disrupt electronics, or worse, pull in energy uncontrollably? National security. Any device capable of absorbing beams might have defense applications. That alone could explain a sudden classification of research. Scientific anomaly. It's possible the results were so anomalous that NASA decided they couldn't be verified. Or worse, they revealed a gap in our understanding too wide to be explored safely. Sometimes, shutting down an experiment isn't about failure. It's about fear. This wouldn't be the first time groundbreaking research disappeared from public view. Nikola Tesla once claimed to have built energy transmission systems far ahead of their time. Cold War research into plasma and lasers was classified for decades. Even today, NASA and DARPA quietly explore propulsion systems we hear about only years later. The Buga sphere may fit into this long tradition of knowledge being hidden until humanity is ready, or until politics decides it's useful. If the Buga sphere, or devices like it, are real, the implications are staggering. Radiation protection. Astronauts traveling to Mars face deadly cosmic rays. A sphere-like shielding could save lives. Energy storage. Imagine capturing beam energy or solar radiation directly, storing it far more efficiently than batteries. Propulsion. What if a spacecraft could absorb particle beams from Earth and use that energy for thrust, like a wireless charging system in space? The line between science fiction and reality gets thinner every year. The story of the Buga sphere reminds us of something essential. Science isn't just about what we know, it's about what we don't yet understand. Maybe the sphere was just an experimental material behaving oddly. Maybe it was the first glimpse of a technology that could transform humanity's future. Or maybe it was something else entirely, something we weren't ready to face. Here's the truth. Every great leap in science begins with confusion, a mystery, a moment where the data doesn't match expectations. The Buga sphere was one such moment. So I'll leave you with a question. Should humanity pursue every strange discovery, no matter the risks? Or are there some doors we should leave closed, at least until we're ready? If you enjoyed exploring this mystery, don't forget to subscribe for more deep dives into space exploration. Like this video if you want to see more cosmic mysteries explained. And comment below, what do you think the Buga sphere really was? Because in the end, science isn't just in the labs. It's in the conversations we share, the questions we ask, and the future we dare to imagine.